Hello dear students, in the today's video session we are going to discuss about the nitrogen compounds. In the nitrogen compound lesson, some book back questions are there, evaluation part questions in the 12th standard Tamil Nadu State Board textbook, in which we can find certain book back questions. For them we are going to write or we are going to discuss the answers. In particular, the question number 8, where account for the following, that is the question, in which 8 questions were given. The first one would be, aniline does not undergo Finkel-Crafts reaction. We should give the reason for this, why aniline is not undergoing Finkel-Crafts reaction. The answer can be discussed as follows. The answer for that is, this is the formula for aniline, the structural formula for aniline, where the nitrogen is containing the lone pair of electron. When this is treated with CH3Cl in presence of anhydrous aluminium chloride, AlCl3. Actually, this anhydrous aluminium chloride, AlCl3, is a Lewis acid. And amine, what we have taken here, the aniline, which is behaving like a Lewis base. So, while treating this with methyl chloride in presence of anhydrous aluminium chloride, in the case of Finkel-Crafts reaction, Finkel-Crafts alkylation or acylation reaction, in which these are the things required. The difficulty is the aniline, in which the nitrogen can donate the pair of electron to this AlCl3, so that the electron density on the nitrogen decreases. So that tends to get electron from the benzene ring. Due to the donation of electron pair, there is an electron deficiency on the nitrogen. So once the ring is having lesser electron density, it do not undergo electrophilic substitution reaction, which means even when you take methyl chloride, AlCl3 can carry this halogen to form AlCl4 minus, and the CH3 is carrying plus. So this will be the electrophile. This electrophile cannot be substituted in the benzene ring, as the ring is losing the electron density, and moreover the nitrogen is donating the electron pair to this Lewis acid. So there is a formation of adduct in between the NH2 and then AlCl3. That might be explained as follows. Yes, we might be getting an adduct like this, NH2 and AlCl3. It is donating the electron and this is receiving the electron. So this adduct do not undergo further action with the methyl chloride, which means that is not answering for this Finkel-Crafts reaction. Is it clear? Simply the reason is, it is a Lewis base and this one is Lewis acid. There is a formation of adduct in between those two, and that will account for the first division. Likewise, if you see the second one, yes, you see the second part, diazonium salts of aromatic amines are more stable than those of aliphatic amines. I am writing the formula for aromatic diazonium salt. It might be the formula for that. It carries plus and is carrying minus. benzene diazonium chloride, and this is an aliphatic diazonium salt. Okay, and you can have methyl diazonium chloride. This is phenyl substituted compound, benzene diazonium chloride. Yes, when you take this benzene diazonium chloride, it's a structural format for that. I am writing the diazonium ion as follows: N triple bond N. This nitrogen is going to carry a lone pair of electron, and this is carrying the plus, and Cl minus is there. So the Cl minus is ignored, means this is a benzene diazonium part, aromatic diazonium part. The diazonium salt in which, as the nitrogen is carrying the positive charge, the pair of electrons tend to move like this, and the bond in between these two breaking up, and the nitrogen is going to carry minus. Execute the change and find a result. This will be the resonance structure. What we are expecting here, there will be double bond N plus, here it is double bond, nitrogen is carrying minus due to the breakup of bond in between these two. When you break this particular bond, when the electrons are migrating there, it carries plus. And in order to compensate this positive charge when the electron pair is moving here, you can have the other resonating structure, or the resonance structure N plus double bond N minus with the additional pair of electron. Now due to the breakup of this bond, this position carries plus. To compensate that, this pair of electron is moving now, so that we can have the other structural formula. This is the structure what we are expecting. This position is carrying plus. Now the bond breaks up and electrons are available for that, and this pair of electrons is moving back, so that we will get the original structure. It clearly indicates that due to this resonance, this is what is known as resonance, which is possible in the case of benzene diazonium salt. So the resonance stabilization is possible, and due to this resonance stabilization, aromatic benzene diazonium salts are more stable. And we know that the stability of these substances increases with increase in the number of resonance structures. Here, these are the various resonance structures possible for the particular diazonium salt. But in the case of aliphatic amines, we don't have such kind of diazonium, or we don't have such kind of resonance structures. And this is the explanation, and this is the account for the second subdivision. And likewise, we are given the other one. See, the pKb of aniline is more than that of methylamine. pKb is a parameter which decides the strength of base. pKb is lower, means we can say the strength of base would be greater. In opposite to that, when the pKb is greater, means we can say the strength of acid would be, or sorry, the strength of base would be lesser. So pKb is deciding whether the base is stronger or weaker. Greater the value for pKb, lesser will be the basic strength. Lesser the value for pKb, greater would be the basic strength. What do you mean by this pKb? pKb is nothing but negative logarithm of Kb. What do you mean by Kb? It is the dissociation constant of a weaker base. Here in the question you are given the aniline. What's the formula for aniline? This is the formula for aniline, C6H5 NH2. Okay, aniline. Suppose if it is in contact with the acid like HCl, then what happens? It can donate the pair of electron to this hydrogen. And we are getting this ion C6H5 NH3 plus and Cl minus. But here the nitrogen is failing to donate the electron to the hydrochloric acid. So the chances of protonation, which means addition of H plus, is lesser. So it is not a good base. Why? Because in the case of aniline, the electron pair present on the nitrogen is used to bind the ring structure. That leads to the resonance. That's the reason why the aniline is lesser basic in its nature. Suppose if it is readily giving the electron pair to the hydrogen plus, the concentration of this, the ammonium chloride ion, phenyl ammonium chloride ion would be greater. So we can expect greater value for Kb. Greater the Kb means greater will be the strength of base. Here the Kb value is lesser. Suppose if you want to find the Kb, that becomes C6H5 NH3 plus and Cl minus divided by C6H5 NH2 and then HCl. The chances of protonation is lesser, so the concentration is lesser. And actually this is greater, the concentration of aniline. And that's the reason why the Kb value is lesser. When the Kb is lesser, we can say the basic strength is poor. Ultimately, that can have greater pKb value. But if you take any aliphatic amine, the aliphatic amines in which the nitrogen can readily donate electron pair to the acids, so that the concentration of product will increase, so Kb value will increase and basic strength will be greater. When the Kb is greater, pKb will be lesser for aliphatic amines. And this is the reason for this particular case. Is it clear? And we are finding the fourth division. Just observe the question, what is given there. Gabriel thallimide synthesis is preferred for the synthesis of primary amines. And it is not holding good for secondary and tertiary amine. And we should give the explanation for that. You must recall what is called Gabriel thallimide synthesis. We should take the thallimide. This is a formula for thallimide. NH. Now that should be treated with KOH in the first step. H combined with OH. As a result of that, we will be expecting potassium substituted thallimide called potassium thallimide. Further, this is to be treated with the alkyl halide RX, where K combines with the halogen atom, so that we will be getting this product C double bond O N R, C double bond O N R. This compound is called as N-alkyl phthalimide. This N-alkyl phthalimide on subsequent treatment with the KOH, two molecules, potassium hydroxide. Then what happens? This part is removed as a primary amine and we are expecting RNH2. Suppose if you want to get the secondary amine and tertiary amine, we are expecting two alkyl groups here, but it is impossible to have two alkyl groups there. So it is an exclusive method for obtaining the primary amine. As we don't have any other alkyl group in this attachment, we cannot obtain the secondary amine as well as tertiary amine. So it's a preferential method for obtaining only the primary type amine. Is it clear? Yes, the other division, ethylamine is soluble in water, whereas aniline is not. What's the reason for that? This is the reason for the fifth division. The answer part would be ethylamine is the formula CH3CH2NH2 and aniline C6H5NH2. This is soluble in water. But this is not soluble in water. Why? The reason is very simple. In the case of ethylamine, the nitrogen is containing the lone pair of electron. Suppose if it is dissolved in water, there is a chance of hydrogen bonding in between these two. Nitrogen can able to donate the pair of electron to this hydrogen, and there is a chance of hydrogen bonding in between the water molecule and aliphatic amines. What are all the organic compounds which are capable to make hydrogen bonding with water? They are all water soluble. But see, the aniline, it is containing the lone pair of electron, and we know that the lone pair of electron present in aniline, particularly on the nitrogen atom, is used up by the ring structure, and it might not be available for the formation of hydrogen bond. So there is no hydrogen bond in between these two. So it is failing to make hydrogen bond with water, and hence it is not soluble in water. Okay. Likewise, the other part, see the other question. Amines are more basic than amides. Amines are more basic than amides. Amines are having this general formula RNH2. The lone pair of electron is there. The alkyl group is electron releasing group. So that can release electron towards the nitrogen atom. So the electron density on the nitrogen atom may tend to increase. So it might be a better donor, best donor, and behaving like a Lewis base, ready to donate the electron pair. It will be a good donor of electron pair. But you see, the amide having the following formula, RC double bond ONH2. It's a formula where the oxygen is electronegative. We know it is carrying slight minus, and due to that the carbon is carrying slight plus. Due to that electronegativity difference, in order to compensate this positive charge, a pair of electrons will be moving like this. The existing bond breaks up. So the electron pair on the nitrogen is delocalized in between the nitrogen and oxygen, and hence the tendency to donate electron pair decreases. So it is not a better base, it does not behave like a base, and this is the reason why aliphatic amines are more basic than the amide. In the case of amide, there is a delocalization of electron, which means it is moving here, there is a double bond and the bond breaks up and opened, it is carrying minus. If it is moving back, we will get the original structure. So it's a poor donor of electron pair. Okay. And likewise the last one, in the question number 8, this will be the last part, where you are given that, just go through the question carefully. Although the amino group is ortho and para-directing group in electrophilic substitution reactions, if you take aniline on nitration, that is giving substantial amount of meta-nitroaniline rather than ortho and para. Why? Take aniline, it is a formula for aniline. When this is nitrated by using the mixture of concentrated HNO3 and concentrated H2SO4, from the acidic mixture you will be getting the hydrogen plus. Now the nitrogen is giving the electron to this hydrogen plus. So due to the protonation, we can have a anilinium ion. This is the ion called anilinium ion. The formation of anilinium. It clearly indicates that the pair of electron on the nitrogen decreases. So electron density is not there. To compensate that, this pair of electron will be moving. So in the ortho position, ultimately, what will happen? There may be double bond in between these two. Okay. And this position is going to carry plus charge. Why? The pair of electron is moving towards this side. So this ortho position is losing the electron density. Electron density decreases in this ortho position, which means this NH3 plus is deactivating the benzene ring to undergo the electrophilic substitution reaction. In the next chance, when the electron pair is moving here, we will be getting the poor electron density in the para position also. So the electrophile cannot be directed towards the para position. The one and only chance, in the meta position, we can able to do the substitution of nitro group. So finally we can have the meta-nitroaniline. The one and only chance at the end, we might be getting the meta-nitroaniline. The reason is, in the case of ortho and para position, the electron density decreases and those positions are carrying positive charge. So the electrophile like NO2 plus cannot attack this positive charge. The free position is attacked by that. So meta position might be attacked by that. Is it clear? So these are all the important things given under the question number 8. In our subsequent video sessions, we are going to discuss about the answers for the other questions which are printed there. Okay. Thanks for watching.